Hi, my name is Bill Cordua. I'm a geology professor associated with the University of Wisconsin-River Falls. Today we're in the little town of Rock Elm in eastern Pierce County, Wisconsin. Looking out across this landscape, it isn't clear at first that anything unusual happened here. It looks like nice western Wisconsin farmland and forest land. Yet, as we'll see, there's evidence that something extraordinary happened here. If we look at the bedrock that outcrops here and there, we can piece together a picture of a major extraterrestrial impact, an asteroid-sized mass of rock or perhaps an icy comet impacting here at supersonic speed. So let's go look for clues in the rock that reveal evidence of this extraordinary event. I'm along Highway 72, not far from Ellsworth, Wisconsin, along the edge of the Rush River Valley drainage. Behind me in this little road cut, you can see some of the normal bedrock for our area. We call this limey rock the Prairie du Chien group, and it's widely exposed all through the river valleys in western Wisconsin, a very common formation. These rocks were laid down about 480 million years ago in a layer cake fashion, and that means that they're deposited as nice flat layers which are traceable for many, many miles throughout western Wisconsin. You can see behind me these rocks are in their original horizontal position, the way they were laid down first when they were limey mud on the seafloor. This means they can be found at predictable elevations all through our region. But these are the last normal rocks we're going to see in this film, because if we go to the east a few miles, we're going to either find the normal rocks are removed, or they're bent up, or they're all broken out of shape. We're along a little road cut along County HH. At first this really doesn't look like very much until you start digging around in it and find out that it's made of very soft clay material. Not at all like the very hard limestone we saw in the previous stop. And that limestone is what should be here given normal geology. You find this flaky, softer rock called shale. It's solidified layers of clay and silt. It's this material that gives our region its heavy clay-rich soil and causes a different land use for the Rock Elm area compared to the surrounding country. We can see this formation much better if we go to a borrow pit a little ways away from here. We're in a small borrow pit a little north of the previous outcrop where the nature of the Rock Elm shale is very easy to see. In the walls of the pit you'll notice that it's a very soft rock, but it also contains some harder layers of siltstone, and you can also see the layers are horizontal. It's not a good idea to go back into the pit for a couple reasons. First of all, it's private property, and second of all, the walls are very unstable and subject to collapse, so it's a rather dangerous place to go. Notice the horizontal even layers as shown on the pit wall. And notice the bands of more resistant siltier rock. Why is there shale here, and when did it form? And where did the normal hard limey rocks of the Prairie du Chien group go? There are fossils in this rock that tell geologists that this was a deep, fairly calm sea that accumulated in a basin about 4 miles across. A particularly useful fossil found here are the ones called conodonts. These are tiny jaws of small marine worms. They're very useful in determining the age of the shale. It tells us that it was deposited between 450 and 500 million years ago, filling a basin formed in the Prairie du Chien bedrock. But why are the hard limey rocks of the Prairie du Chien group missing here? And what forms a circular basin 4 miles across in which shale could accumulate? There's a little bit more evidence if we look at some outcrops just up the road. We're a bit uphill from the shale borrow pit, and we can see that the shale is graded upward into a much coarser, harder rock here. This is a sandstone, and this sandstone also contains marine fossils. That tells us that the little marine basin here was filling with sediment, first shale on the bottom, and then coarsening upward to sandstone as the water got shallower. Sandstone is rather common in western Wisconsin, but this sandstone is unique. First, notice that it's hard and not crumbly like so much of our local sandstone. Much of our sandstone in western Wisconsin is made of nearly pure quartz-sized sand grains, as seen in this highly magnified view of sand from the St. Peter Formation that's well exposed in the River Falls area. The Washington Road sandstone in Rock Elm, however, has angular grains and contains a lot of feldspar and mud. It's very different from the sandstone formations elsewhere in our area. It's clear that we have a basin here about 4 miles across that's being filled with seawater that either was never deposited or is not preserved anyplace else in this region. There's still more clues to the origin of this circular anomaly, which we'll see at our next stop. Nugget Lake Park is a really neat county park. that holds some key outcrops. We're going to visit the best one, which is called Blue Rock. We're at Blue Rock at Nugget Lake Park, where we see a large outcrop of Prairie du Chien dolostones. This is the same formation that we saw at the very first stop. However, unlike those rocks, which are horizontal, these are tipped at quite an angle. In fact, they're warped into a bend us geologists call a syncline. You can see how the layers bend down and then flatten out and come up again, making the U shape of the syncline. The rock is also quite fractured internally, and this tells us that some powerful force acted on it after it was deposited. There are the bent and broken bedrock masses of the Prairie du Chien group along both the north and south edge of the basins. What they suggest is whatever event formed the basins threw these rocks and shoved them to the side so they were bent up, at which point then they then slid into the developing basin. I think we see now that this basin was not formed as a result of some slow, gentle subsidence, but rather the result of some violent event which threw a lot of the bedrock aside, shoved other of the material to the side where it could slump in. There's one other place we're going to look for clues, and that's right in the middle of the structure, what we might call ground zero. The middle of the rock elm anomaly is marked by a group of tree-covered hills, as we see here. This is all private property and should not be entered without the owner's permission. There actually isn't much to see unless you're a trained professional. The middle of the structure does hold a surprising structure, a number of outcrops of tilted, pebbly sandstones. These occur in a circular region about a half a mile across. Work shows that this is a formation called the Mount Simon Sandstone, named for a locality in Eau Claire, Wisconsin, where it's exposed to the surface. Here, though, in this county, it should be hundreds of feet below the surface, and yet here it is, right up atop, tilted and pushed up, well out of its expected position. We see this basin has a more complex shape, pretty much like this angel food cake pan. It's deep, it's circular, but it has a high spot that comes up in the middle. It was this shaped basin that filled with shale and sandstone as the sea flooded back into the area. That shape is a giveaway to the origin of this anomaly. It has all the features of a classical, large meteor impact crater. We can see impact craters on the moon, where craters can survive unchanged for a long time in a stable, airless environment. In this photo, we see this crater, which is Tycho crater, has a circular basin, a central uplift in the middle of the crater, and blocks that have slumped into the crater around the edge. Rock Elm would have looked like this when the seas bringing the shale and sandstone sediments came in. Well, we're back here on the south edge of the structure. If we look north, we can see all the critical features of this anomaly. They're labeled for you on this next photograph. The south edge of the structure is a downhill dip in the road to the left. The northern rim is near the farmhouse way out on the horizon. The green hills in the middle of the central uplift, and the low areas are underlain by the shale and sandstone of the basin fill. I had the fun of walking the area and figuring this structure out a number of years ago. This geologic map shows the structure, which is now officially named the Rock Elm Meteorite Impact Structure. The pale blue and dark yellow are the normal rocks outside the structure. The central uplift is shown in pale yellow. The green is the deformed rocks such as we saw at Blue Rock. The darker slaty blue and olive green are the shale and sandstone that filled the basin. So far, we are inferring a meteorite impact origin for this feature based solely on the shape or the morphology, but there's actually much better evidence in the rocks that we'll see next. Firm evidence for the impact origin of the Rock Elm feature came from the work of the Smithsonian Institute and NASA meteorite expert Dr. Bevan French. These are highly magnified views of sand grains from the rocks of the central uplift. Dr. French documented unique fracture patterns in the quartz grains of these rocks, ground zero as you may recall. Experiments show that these sorts of fractures can only be produced by the sort of shock waves coming from an asteroid impact. By assuming the impactor was typical of asteroid bodies in terms of velocity and density, Dr. French was able to suggest some aspects of the impact. This event was similar to, but smaller than, the impact that caused the Cretaceous tertiary extinction, the dinosaur killer, as shown in these paintings by William K. Hartman. According to Dr. French's model, this impactor was about 200 meters in diameter, or twice the size of Lambeau Field, and was traveling at a speed of 12 miles per second. Its impact energy would have been equivalent to 63,000 Hiroshima-sized A-bombs, but no radiation. Clearly you wouldn't have wanted to be here then. The middle of the structure rebounded to make the smashed rocks of the central uplift. Masses of rock were crushed to the side and then slid back into the crater, making features such as blue rock. When the dust cleared, the sea flooded back into the crater, leaving behind the shale and sandstone we see as the crater filled with sediment. That accounts for the odd geology we see in the Rock Elm area. This show demonstrates how geologists can solve a mystery by using the clues they can find in the rocks. There's a field guide to the Rock Elm Meteorite crater that I co-wrote with one of my former students, Amy Neighbor. It is for sale at the Nugget Lake Park office and directs you to a lot of critical outcrops exposed in and near the park. This park also has many other attractions, including a nice campground and lake for boating and fishing. This is a great place to enjoy the outdoors and also learn some really interesting geology.